So design principles. So it's not kind of design principles, but things that you can think about doing. So having a project notebook. So if you've kind of worked in a company, you've probably been kind of given a notebook, and they'll ask you to record everything, all the experience you've done, and kind of date it. And the same sort of true of most kind of robotics projects. So certainly, if you look, Kai has quite a nice notebook with kind of loads of sketches in. So it's kind of whenever you have an idea, kind of you can jot it down. If you have an experiment, you can jot it down. Even experiments that don't work, note them down so that you can refer to them later on, maybe kind of a few months down the line, or maybe even kind of more than that. And also always take pictures. So yeah, So this is just an example for a project that I'm doing in third year. So the second of the 3 points that I just kind of want to make kind of at the start is that a lot of people, when they design something, they go, oh, I'm designing something, let me turn on SolidWorks, let me stare at a screen. That's kind of a form of procrastination. It's CAD isn't actually going to help you design something. It's going to be far faster if you just sit down at a notebook, start sketching your ideas out, and then keep sketching until you have a pretty good idea how it's going to look, and then go on to CAD. That will be far faster than doing some stuff on CAD, then realizing it's not quite going to work, and then working it through. And kind of linked to this, again, a lot of people go, oh, I need to 3D print stuff. 3D printing takes a lot of time, and that's another sort of delaying tactic. And the third thing I would say is there's a tendency to want to combine things, to kind of make things simpler by combining things. So this is an example of a project that I was involved with a few years ago that was to make a robot that could kind of shift cubes. And we thought it would be a great idea if we combine the shell of the robot with the printed circuit board. So all of the circuitry, that the electricity that was running the robot was going through the sides, was etched into the copper plate on the side of the robot. And that actually turned out to be really stupid. The robot didn't really work that well. And because you were trying to combine these two functions of something that could channel the circuit and the frame, and so always think of separating functions. And the same's true of even of just bolting things on. You probably want something to actually to secure it in place. So if you were putting a rectangle down, maybe a rectangular hole, so you put it in the rectangular hole and then you can bolt it down, rather than just using the bolts as the thing to guide where it's going. So kind of three overarching things are: think about having a notebook, sketch before you turn on CAD, and then also just think simplicity. And simplicity doesn't always mean, oh, I can combine everything together. So materials. So I think there's three main materials that you could use at home. Wood. So wood comes in kind of three flavors, kind of in the Dyson Center. So MDF. So the advantage of the MDF is that it tends to be quite flat, certainly compared to plywood. So MDF is just kind of mushed up kind of wood with some in resin, and it's kind of pressured together. Plywood is different layers of wood stuck together in different kind of orientations, and plywood often tends to be a bit warped, and certainly if it's been left lying around. And there's also pine wood, and pine wood again, it can also be a bit warped. So MDF is heavier than plywood. So I of these materials, if you want sheets, then probably MDF will be flatter, but it'll be slightly heavier. And if you wanted kind of structural supports, then maybe pine wood. So you could use aluminium angle to combine size, so that's plywood size, and you can bolt them on. Or you could actually use pine wood as to create the main structure and screw it together. And actually this is quite a fast way of doing it. You don't actually need to do any CAD models to make a robot like this. And the nice thing about wood is you can just, you need to drill a small pilot hole with something like this, but you can look up online the size of the hole that you need for a specific screw. But once you've done that, you can just start to stick things together actually quite quickly, um, and um, and you kind of avoid the need for 3D printers. So if you want to stick a motor on, you can just screw it directly in to the pine wood, for example. So it's quite a quick way of doing things, and yes, cutting the wood as well. It's relatively fast. So the second material that you could look at is plastic. So plastic, mostly in the Dyson Centre, it's things like acrylic, because when you laser cut acrylic, it's got the special property that it kind of vaporizes when the laser hits it. So it looks very nice, but actually, I wouldn't really look at using it at the home because it is quite brittle, and actually to make these little holes in it, you're probably going to end up cracking it at some stage. But if you do want a pane of it or a nice rectangle somewhere to make it look nice, then I think that'd be fine. But making something as complicated as a laser cutter, unless you've got a laser cutter at home, it's going to be tricky. And then metal. So I think metal's harder to use than wood for a whole series of reasons. Now, if you're an engineer, you'll have done the structural design project where you build a bridge, and actually to get the holes in the right place is actually far harder in metal because it's a harder material. Your drill will shift a bit, and that means in a robot, if one wheel is slightly in front of the other, even if it's by 0.5 millimeter or even 1 millimeter, that will have kind of effects over a long distance. So this is a robot that was I didn't build, but the year above me at school built, and that had a lot of issues because the metal wasn't quite right. But you can get you can use things like aluminium extrusion or robotic kits, which will be to the right dimensions. But I think metal is a harder material than wood to get accurate, and it will cause you problems because of that. And also the metal is more flexible in some ways, which I mean you find out in the structural design project because you build the bridge and then you bend it. So those are the three materials that you can think about. Yeah. So if you want to move stuff, there are kind of two main methods. So there's a threaded rod, which is a bit slower, or that you can use a pulley and timing belt. And pulleys and timing belts are kind of the bread and butter. You tend to not see some sort of gear-on-gear movement. You can print, if you have a 3D printer at home, you can print pulleys like this, or you can buy them online. I'll talk a bit about that later. So yeah, electronics. So there are kind of three flavors of motors that you could look at. So a stepper motor is what you have in a 3D printer. So it steps through a number of cycles and it knows the position it's turned through. They tend to be a bit clunky and big. Servo motors know the position they've gone to. So you had those little small blue ones last term, but they can be far bigger. And the other type of motor that you can use is a DC motor with some sort of encoder. If you just have two DC motors, they won't really know where they're going by themselves. So yes, you can put an encoder on, and that will kind of measure how far it's gone. Yeah. So soldering. Yeah, I think. Yeah, I think there's some quite good videos on this online. It's kind of worth possibly kind of touching on. Well, which type of solder you use? Because in the Dyson Centre, I think they naturally have non-leaded solder. So and that's because you're not meant to put lead into the environment, but non-leaded solder actually is not really that good for the body. It irritates the eyes, and it's kind of hard to use. It's got a higher working temperature, and it's hard to know if it's formed a proper electrical contact. Lead, although it's actually slightly better for you in terms of it doesn't create that. Non-leaded solder has a flux in it, which is what is bad for you in it, which is a kind of acid type thing. But leaded solder doesn't have that, but it's lead, so it's not, shouldn't be licking it. But it's easy. Lead work has a lower temperature and it's easier to use. So if you're at home, I always use lead because it's easier to use. It creates a shiny surface when it's created a proper contact. And it's also safer for me as a person. If you use non-leaded solder for a long time, it has a serious health risk just from the acidic fumes you don't get with the leaded solder. So at home, you can, if you have a soldering iron, you can use strip board or vero board. So strip board is just strips of copper, and you poke things through and you solder them, and the strips of copper mean that things can conduct along, so you can put multiple components in. If you want to do that over a slightly smaller area, you can use something called vero board, which is just has these little electrical contacts, and you have to put the solder between the contacts to connect things up. But what it means is that you can work in both X and Y. So normally, if you want things over a slightly smaller area. Molex connectors. So if you've got wires coming into a board from maybe a motor or a sensor, but you want to be able to detach that sensor to test it out, then you can use Molex connectors. So you can get these little clips and use a pliers to kind of push the tabs in and then solder it, and then clip it into the connectors, and use those to kind of connect your motors and your sensors to a main board. You had kind of jumper wires last term, but you can also buy jumper wires like this, which are at kind of set lengths for strip boards. So this is the sort of thing that you can create relatively quickly at home if you have a soldering iron. And soldering irons aren't that extensive, so you've got the Molex connectors, and you've also got these jumper wires coming in, just soldered directly in, and jumper wires on the board. So if you have exposed wires, you can use heat shrink to cover them. So you could use electrical tape, but you can also use heat shrink, and it's just a cylinder of plastic, but you can use a hot hairdryer to melt it, and it just shrinks with heat, and that can cover just exposed electrical parts. Say if you've got a red and a black wire going into a Molex connector, you don't want one of them to touch the other, so you could use heat shrink on it. So often you'll end up with a lot of cables wandering around, and you don't know what to do with them. So there's a number of ways you can deal with them. You could put heat shrink on bunches of wires to put them together. You could tape bunches of wires together up. You could use cable ties to bring wires together. So there's some cable ties here. But one of the methods that I kind of quite like is using this kind of wire-o kind of cable tidies that you sometimes kind of and those you can just wind on. So even once you've done the wiring, you can wind these on, and then use these things which have a sticky pad on the bottom and a cable tie to kind of clip them to the sides of your robot. So I think in about a week's time, Richard is going to talk more about PCBs. But in terms of the sort of PCBs that you could have, is this sort of thing. You have a your some sort of or you have your Arduino Uno in the center, and then the circuitry takes that out to various Molex connectors, which you can then plug your sensors and your motors directly into, and you might need some resistors, for example, between your sensors and the Arduino. So that's the sort of thing that you could make in terms of the PCB. But I think Richard's going to talk more about that in a week's time, and so you then create circuitry like this. Yeah. So testing. So testing robots is a bit like kind of any sort of thing in life. It's testing until you know it can't go wrong. Yeah. So that might include, well, it probably includes creating a full-size arena so that you can test your robot again and again and again and again and again until you know nothing can go wrong. Yeah, so this is actually the last section, so I've gone through it slightly faster than I thought I would. So buying stuff. One of the main places you can buy stuff is RS, and they normally deliver on the following day. So it's a very easy website to use. It's quite fast. But there's others. So these tend to be slightly harder to use, take slightly longer, but they do have slightly more stuff on them. So RS, although it's expanding, it sometimes doesn't have everything. So you can look at these. So sites like Farnell, their search systems are really aren't that good. It's kind of and then if you want tools, you can go. Screwfix is quite good. You can go in and if you want any sort, if you want a drill or something, then you can just go into there's a Screwfix near the station if you're still in Cambridge. And there's also Mackay's, which is sort of kind of you go past Jesus and kind of go a bit further, which also kind of sells these sorts of tools. So in terms of the toolbox, mechanical things. So you might want a fret saw. So a fret saw allows you to cut curves or holes or just kind of inside shapes of any form. So it's got this. So if you had a sheet and you want to cut a curve around it, or you want a strange shaped hole in the middle, you can put you can drill a hole and put the wire in, and then cut around. Drills, clamps, a hacksaw, the calipers, yes, yeah. And then electrical stuff, I think it's mostly covered. You might also want a multimeter, pliers for bending the Molex connectors, yeah, leaded solder, kind of multi-core, maybe a wire stripper, solder wick, which is a kind of copper mesh which can wick up the solder. Yeah. So yeah, I think that's actually everything. So I've gone through that relatively fast, but the main kind of message is to kind of keep things simple in the design. And I would add this that sort of also means asking yourself, do I need to CAD it all up now? The answer is probably no. Can you actually do everything without doing CAD? The answer might be yes if you keep it simple enough. So I think of that, and also just looking at what's already out there, and if someone's already done something, just kind of copying that. But I think that's everything from me. So I'll stop sharing, and you can ask any questions if you have any, or you can write it in the chat.